Alright, welcome back to part 2. In this video we're going to differentiate the exponential function. So if the exponential function, which we'll call y of x is equal to e to the x, we showed in the last video that that's actually equal to the sum from k equals 0 to infinity of x to the power of k divided by k factorial. And in case you've forgotten what that means, I'm going to write it in a nicer way. This is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4 divided by 4 factorial plus ... In other words, we keep adding these things on forever. Well, we don't do it forever. We keep adding these things on, and we see what number does this get closer and closer towards. That's whatever e to the power of x is. And we do that for each x. That's how we get the value y of x. Okay, well now we're going to define the function yn of x. Yn of x is going to be a lighter version of this. We're only going to sum it up to n terms. So yn of x is going to be 1 plus x, it's a horrible plus, is going to be 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4 divided by 4 factorial plus ... plus x to the n divided by n factorial, actually. So we're going to stop it there. That's where the yn of x ends. And now we're going to differentiate yn of x. Notice that yn of x is actually just a polynomial. Something times 1 plus something times x plus something times x squared plus something times x cubed plus something times x to the 4 all the way up to something times x to the n. So it's just a polynomial. And polynomials are really easy to differentiate just using the power rule. So let's go ahead and do that. Yn prime of x, well, what's going to happen? The 1 disappears because the derivative of a constant is 0, because a constant function is not changing at all, and therefore the rate of change is 0. So the 1 disappears. The x becomes a 1 because the derivative of x is 1. And now let's differentiate the third term rather. So to differentiate it, we bring the 2 down, subtract 1. And so we're going to get 2 times x to the power of 1, which is just 2x, divided by 2 factorial. But 2 factorial is just 2 times 1, or in other words, 2. And so those 2's are going to cancel out. So we're just actually left with x at the end of all that. Same deal again. Let's differentiate the third part. So plus, let's bring the 3 down. So we're going to get 3x, and we have to take off 1 from the power, so 3x squared divided by 3 factorial. Well, 3 factorial is actually 3 times 2 times 1, so 3 times 2 factorial. Well, in other words, these 3's are going to cancel off, so we're just going to be left with x squared divided by 2 factorial. Plus, and I'm sure you can see where we're going with this, but let's do it on the fourth one just in case. So we'll bring the 4 down. So 4x to the power of 3 divided by 4 factorial. Well, 4 factorial is actually just 4 times 3 factorial, and those 4's cancel. So we're just left with x cubed divided by 3 factorial. X cubed divided by 3 factorial, and so on. And we keep doing this all the way up to, well, we'll differentiate the nth term, and we're going to get x to the power of n minus 1 divided by n minus 1 factorial. So this time it cuts off at n minus 1. So yn prime of x is actually equal to yn minus 1 of x. And an important detail to note here is that yn of x minus yn prime of x is actually equal to x to the power of n minus 1 divided by n minus 1 factorial. No, that's wrong. yn of x minus yn prime of x is going to be equal to that guy there. That's the one that's going to remain. All the rest of them will cancel off. So it's going to be equal to x to the power of n divided by n factorial. Now, for any x, as long as x is fixed, as n gets bigger and bigger, as n gets bigger and bigger, as n tends to infinity, this thing here is going to tend to 0. That thing there is going to get closer and closer to 0 because n factorial gets really, really big, much bigger than anything to the power of n for large n. So this thing is pretty much just going to go bye-bye as n gets bigger and bigger, and we're basically going to have that, well, basically yn of x gets closer and closer to its derivative. That's what that's saying. Now another thing to observe is that as n gets bigger and bigger, yn of x gets closer and closer to y of x. As n gets bigger and bigger, yn of x gets closer and closer to y of x. So let's write down what we have. Yn of x gets closer and closer to y of x as n tends to infinity, and yn prime of x gets closer and closer to yn of x as n tends to infinity. And now this is the result is not always going to be clear from this. However, there's a pretty powerful theorem, and I guess for now you're just going to have to take it as fact. Basically, the theorem says that as long as this limit here exists, as long as these yn functions are getting closer and closer to some function, and as long as these things converge nicely, so these things have to converge nicely, they have to get closer and closer to something in a nice way. As long as that happens, we can actually say that y prime of x is actually equal to the limit as n tends to infinity of yn prime of x. So y prime of x is equal to the limit as n tends to infinity of yn prime of x. And so, while the limit as n tends to infinity of yn prime of x, well, yn prime of x is this guy right here. As n gets bigger and bigger, that thing is just going to get closer and closer to y of x up here. It's going to get closer and closer to y of x. So actually, y prime of x is just equal to y of x. So y prime of x is just equal to y of x. You can find that theorem I'm talking about somewhere on the Wikipedia page for uniform convergence. If you're looking for that, it's in the differentiability section. Okay, so actually, let's rewrite it one more time, just for the sake of completeness, because this is a pretty powerful result. If y of x equals e to the power of x, then y prime of x is equal to y of x, which is equal to e to the power of x. In other words, e to the power of x differentiates to itself. So it's a function that when you differentiate it with respect to its input variable, you get the same function again. That is pretty bizarre. Anyway, that is the main result here. You need to know this. This is very important. And that's all for now. Don't forget to check out the notes on differentiability of exponential and logarithmic functions. See you next time. Thanks very much for watching. Take care. Bye.